Alrighty, so we are going to continue working here now and move on to two means. And this is going to be in two sections because we have both dependent samples and independent samples here when we come to means. So our proportions are solely independent samples. Our means are going to be both, and depending on which one they are going to do a slightly different process. This first section, like I said, is going to be matched pairs. So we will do our hypothesis testing for them and then go and construct our confidence intervals for our matched pairs. Starting with our hypotheses. Statistical inference methods on matched pairs data use the same methods as a single population mean, except that we are working with what is called the difference. We're going to work through a full example to kind of explain how that works, and you'll see. In order to test matched pairs, we are going to see that the following happens. The first is that it's random sampling, and they are set up as matched pairs or dependent samples. So what that means is there is a relationship between the first and the second individual, or an individual is paired with themselves. That makes it a matched pairs, and you just make sure that, of course, those people were randomly sampled. We want to make sure that, of course, these are dependent samples. We want to make sure that they come from a normally distributed data set, or that the sample is greater than 30. And our samples are, of course, no more than 5% of the population. So the way we're going to do this is set up, of course, our hypotheses. And this is going to say mu d, that stands for the mean difference. Our null is always equal to 0. And then our alternate is the three choices, not equal to, less than, or greater than. We select our level of significance. We will then use our technology to get us a p-value. We will check to see if p is less than alpha. If it is, we can reject the null. If it is not, we do not reject the null. And we, of course, then write our conclusion. These procedures are called robust, which means that if we have a little bit of deviation from normality, we'll still have good results. However, if our data does have massive outliers, we really shouldn't use this process. Here's a full example. I'm going to show you how the entire process works, and then, of course, how we would do all of it in StatCrunch. So Professor Andy Neal measured the time in seconds required to catch a falling meter stick for 12 randomly selected students' dominant hand and then their non-dominant hand. Professor Neal wants to know if the reaction time in an individual's dominant hand is less than the reaction time in his or her non-dominant hand. A coin flip is used to determine whether reaction time is measured using the dominant or non-dominant hand first. We're going to conduct the test at an alpha 0.05 level of significance, and the data is on the next slide. We have 12 students listed here. We have their dominant hand reaction time and their non-dominant hand reaction time. And remember that these were randomized as to which one was done first based on a coin flip. So the process of doing matched pairs here, you can see that this student's dominant hand is paired with their non-dominant hand. So these are paired data. The process for doing matched pairs is you compute the differences between the two of them. So you take the first one minus the second one, and that's going to give you a difference. If the difference is negative, that means that this first one is smaller than the second one. If they are around 0, then they will be about equal. And if it's positive, then this first one will be bigger. We want the differences to be negative because of what we were asked. We were asked, is dominant hand have a quicker reaction time than non-dominant hand? We want to know if this one's smaller than that one. Okay. So this is actually then what your hypothesis test is based on, is these values here, these difference values. What would happen is in StatCrunch, we would use this entire column here and calculate its mean and standard deviation. So mean and standard deviation. And then we verify here that we would have a normal data set with no outliers. So what we're going to do is we're going to look at what's called a normal probability plot and or the box plot. So there's two ways that we can look at this. We've got two things here. This is the normal probability plot, and then we have the box plot. And one thing you can do is there's a table you could look at to make sure, hey, is this good enough to pass normal? Or you can kind of just look generally at the shape of the box plot and say, hey, does it look normal? Or in this normal probability plot, do I have about the same that are below as I do above? You have two choices. You can look at the normal probability plot or look at a box plot. And if you're using your box plot, you just have to look to see, does it look symmetric enough to say that we would say, yes, it looks normally distributed. Just a process of double checking, hey, can we run the test? Yes, we can run the test. So what's going to happen is we want to test the mean difference is 0, would mean that they're the same reaction time, versus the mean difference less than 0. And if you ever get stuck figuring out how to do that, you go back here. So the difference was calculated as x minus y. So I want x to be smaller than y, first less than second. That is mean difference less than 0. We're doing a left tail test with a level of significance of 0.05. So what I would do is I could then, I'm going to run a paired test, and you're going to have to go to a specific spot in StatCrunch. It's going to be under the mean test, and then we're going to be doing paired. So we will be doing a t-test and paired. I'll show you guys when we do the next one. We would enter our two data sets and then look at our p-value here. P-value is 0.009. P0.009 is less than our p-value. Our p-value, I think we said it was 0.05. Yes. 0.009 is smaller than 0.05. So we can reject the null. Right there, he rejects the null. And then we have enough evidence to conclude that the reaction time in the dominant hand is in fact less than the reaction time in your non-dominant hand. Let's work through some examples from StatCrunch. SUV versus a car. It is a commonly held belief that SUVs are safer than cars. If an SUV and a car are in a collision, does the SUV sustain less damage, as suggested by the cost of repair? The Insurance Institute for Highway Safety crashed an SUV into cars with the SUV moving 10 miles per hour and the front of the SUV crashing into the rear of the car. Every single test was run the exact same way. The car was stopped. The SUV was moving at 10 miles per hour, hit the back of the car. You can see we paired here 1, 2, 3, 4, 5, 6, 7 pieces of data. So the question asks, why are these matched pairs? Why did they go together? You have to tell me, why is this data paired with this data? Well, it's because the two cars that are listed in each row were in a collision together. B says, draw a box plot of the different data, and does the visual evidence support the belief that SUVs have a lower repair cost? We're going to go first to draw our box plot and make sure, can we double check this? Does it look like it's normally distributed? What we're going to do is we are going to go to StatCrunch. Got to get my StatCrunch back up here. And we got SUV and we have car. 17.1, 14.4, 850, 23.29, 14.15, 14.70, 28.84. All right, cars, 12.74, 23.27, 32.23, 2058, 3095, 3386, and 4560. We have all of our data here. There's a few things that we can do. I'm going to kind of show you how this whole entire process works here. We have some choices. Under stat, again, we have a small sample size, 1, 2, 3, 4, 5, 6, 7 data sets. So we're going to go to T-stats. And under T-stats, because remember, we're always going to T-stats for these because our samples are pretty small. We have the option here of paired. So anytime you have matched pairs design, you have to click paired. I am going to have SUV. I'm going to have car. I know we're not doing the hypothesis test, but I'm going to read what it says here because we're going to do all of this together. All right, because it's saying, do the data suggest they want us to run the hypothesis test. So draw the box plot, and we go on, and as the data then suggest, the repair cost for the car is higher. All of these parts get done together. We want to know if car is higher than SUV. Right there, that is my hypothesis. So B, you'll see graph. Null is that the mean difference is 0. The alternate is the mean difference is less than 0. We're going to compare our p-value to our alpha of 0.05. Okay, so let's go back here. Let me get my data table back up. We want a less than test. So what I'm going to show you here, let's have it save the differences. So just so you can see, because I'm going to show you how this entire process can work another way. And then I'm going to have it make, it asks for the box plot, but I'm also going to have you draw the QQ plot. So I'm going to hit shift and arrow down so that it selects both of them. So I'm going to click compute. I'm going to need to make this a lot larger than it is so that you can see what we need here. So first thing that's going to be here is the box plot. And the box plot was asking, is the SUV greater than the car? Does it look like overall we kind of have a SUV is less than the car, which would mean that we end up with a negative result? Well, yeah, if I look here, here's 0. Here's the mean of our data set. Here's 0, and most of my data is negative. So it's looking like this data does have a negative relationship here. So other thing you can do is in the QQ plot here, it's going to graph all of your points and give you a correlation value, that same correlation kind of coefficient that you got when we did linear correlation. So there is a table in the back of your book, which I need to pull up here quick, so I can show you that this is in fact normal enough that we can do it. Remember, we had 7 pieces of data. So I'm just going to show you how they double check in the book that it is normal. There is, I want table 6. Right here. We had a sample of size 7, and this is the critical value you have to have in order to have it be normal enough. So 0.898. I just wanted to show you that we do have enough here with our data set, with ours being 0.95. We do have enough to show that it is there. It asked in B, does it look like the data in the box plot is mostly negative here? And I would say yes. If here's 0, we only have a little bit above and we have a lot below. If we go and look at our hypothesis test here, we go look at our p-value, 0.0181. So yes, mostly negative, 0.0181. Looking at this now, the p-value is less than the alpha value, so we can reject the null. So yes, the data does suggest that the repair cost for the car is higher, the SUV is smaller. I want to show you here why they claim that you could do this as a 1 sample test. And that's why I had it store the differences here. You don't have to normally click that. But what I'm going to show you here is I'm going to run a 1 sample mean test on the differences, and you're going to get the same answer. So T, 1 sample, I have data. We're going to use differences, and I want to know, again, is it less than? So if you look here, we get the exact same p-value. You can use the 2 columns, and StatCrunch will calculate the differences and do all of that as a paired test under paired. Or you can calculate the differences here and then run a 1 sample. And how you get this is literally just 1721 minus 1274. Right there, 1434 minus 2327, and you're writing those answers there. And then you can do a 1 sample test on this data set, and you get the exact same answer that yes, the difference is less than 0. Clearly, SUV takes less damage than a car. The following data represents the daily rental for a compact automobile charged by 2 rental companies, Thrifty and Hertz, in 10 locations. Test whether Thrifty is less expensive than Hertz at the 0.1 level of significance. As note, a normal probability plot and box plot of the data indicate that differences are approximately normal. Most of the problems here will actually tell you, hey, it's already approximately normal, you don't have to check it. But just like all the other ones, any of the ones I give you are going to be able to be done. I'm not going to give you a question here that cannot be done. We want to know if thrifty is less expensive than Hertz. So we want thrifty less than Hertz. Null mean difference is 0. Alternate mean difference is less than 0. P alpha is 0.1. So let's go enter our data and see. So thrifty Hertz. Stats, small sample, stats. So we're going to go to paired. It's the one down the bottom here. I'm going to pull that over. We're doing thrifty and Hertz. I don't need to save the differences. I just need to change my symbol. I don't need to do any of these plots here because it doesn't ask me to do any. So I'm just going to hit compute and look at the p-value here. So the p-value is 0.3364. And p is greater than alpha, so we do not reject the null. So we do not have enough evidence to claim thrifty is less expensive than Hertz. And if you look at it, so here it's greater, here it's less than, here it's less than, less than, less than, less than, greater, 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 greater. I have 1, 2, 3, 4, 5 that are greater, 1, 2, 3, 4, 5 that are less, and those end up canceling each other out. And we'd show that, hey, there's not really a difference here. Next thing we're going to do here, looking at my notes, is we are going to construct confidence intervals here, still using StatCrunch. We will do constructing our confidence intervals for our matched pairs next. Every time we go over these, I show you the formulas. We don't really ever do the formulas, but I will show them to you so that you can see them. Remember that if you were going to do these by hand, you would have to use the table in the back of your book, which is also why, again, one of those things I don't really, it's a lot more extra work than needs to be. And if we've already got our data in StatCrunch, we'll just click the other button to do confidence intervals. Going back to the switching of the ruler with your dominant and non-dominant hand, let's construct a 95% confidence interval. So clearly we did this one in a previous example, so we can just go and get the answer here. Negative 0.0236 to negative 0.0027. What does this mean? We are 95% confident that the mean difference between the dominant hand's reaction and non-dominant hand's reaction time is somewhere between negative 0.0236 and negative 0.0027 seconds. Remember that they're both negative. If they're both negative, both positive, we have evidence to show that one is bigger or smaller than the other one. So basically what that means, because they're negative, your dominant hand has a reaction time between this many seconds faster than your non-dominant hand. So remember, again, if it doesn't contain 0, we do have a true difference between the two. Hardness testing. The manufacturer of hardness testing equipment uses steel ball indenters to penetrate a metal that is being tested. However, the manufacturer thinks it would be better to use a diamond indenter so that all types of metals can be tested. Because of differences between the two types of indenters, it is suspected that the two methods will produce different hardness readings. The metal specimens to be tested are large enough so that both two indentations can be made. In the piece of metal, you'll get a steel indent and a diamond indent, and you will get both readings here. This is why they are paired. We're going to then compare the hardness readings to each other, constructing a 95% confidence interval to decide, is there actually a difference or are they close enough that we could just swap them out? Let's go to our StatCrunch. Everything is paired. So small sample with means t-stats. We are going paired. We are comparing steel to diamond, and we want a confidence interval that is 95%. Okay, so we're right, 95%. Click compute. And here is our limits. So negative 2.48, negative 0.18. Okay, these are both negative, meaning steel is less than diamond. So for less than 0, so overall less than 0, so steel is less than diamond. We can say we are 95% confident the difference in hardness rating between steel and diamond indenters, D-E-T-E-R-S, is between negative 2.48 and negative 0.18. And it doesn't really give me a unit. I'm just going to say hardness. What does that mean? We can be about 95% confident a steel reading is somewhere between negative 0.18 and negative 0.248 hardness less than, or I guess I can, I don't need the negatives there, the diamond hardness. Because I put less than, I don't need the negative there. This is how we write it. We are 95% confident the difference in hardness rating between steel and diamond indenters is somewhere between negative 2.48 and negative 0.18 hardness. What does that mean? We can be about 95% confident that the steel reading is 0.18, 0.28 hardness less than the diamond hardness. Less because it's here and we were testing less, or because they're both negative, it means less. So let me show you again. We can compare this with a hypothesis test. That's why they're all paired together here. So if I open it back up and instead I do a hypothesis test, less than 95% confidence means our p-value is, or alpha is 0.05. And we have 0.01. 0.01 is smaller than 0.05. So it does clearly show that steel gives me a less result than diamond. They do have a different measurement. All right, so I got one more example here. So breaking distance. An automotive researcher wanted to estimate the difference in distance required to come to a complete stop while traveling 40 miles per hour on wet versus dry pavement. Because car types play a role, the researcher used 8 different cars with the same driver and tires. The braking distance in feet on both wet and dry pavement is shown below. Construct a 95% confidence interval for the mean difference in braking distance on wet versus dry pavement, where differences are calculated as wet minus dry. Interpret the interval and note that a normal probability plot says, hey, this is normal. We are doing wet minus dry. And one would assume that it would take longer to stop on wet than it would via dry. Because the same car and driver and tires were used on both wet and dry for each car, car 1. So car 1 had a driver, tires, that is a paired. Car 2 had a different car, but it was the same driver, tires, both on wet and dry. Then they put this third car, the fourth car, fifth car. So each one was paired. Car 1 had the same driver for both wet and dry. Car 2 had a different driver, but the same driver for its wet and dry trial. So stats, paired. I'm comparing wet to dry with a confidence interval 95%. $35, $85. So we are 95% confident. The mean difference in stopping on wet versus dry is between 29.55 and 35.85. Is it feet? Yes, braking distance in feet. Both of these were positive. That means that we can be about 95% confident braking distance for wet pavement is 29.55 to 35.85 more feet than on dry. Clearly, wet took longer than dry because both of them were positive. Wet is clearly larger than dry. And that is, on average, how much longer it takes a car to stop on wet pavement versus dry pavement. Anywhere between about 29 and 35, 36 feet. That is the end of that section. If you ever need me to make some extra examples, I can pull up another homework problem. Just ask and I'll be glad to make another video. We have one more section and then we are done with notes.